Okay, hello. We're going to continue on with Chapter 7 in Chemistry. Corwin, Introduction to Chemistry by Corwin. And last session, we worked on balancing equations, but on this session, we're just going to continue with this worksheet. And the next section on the worksheet has to do with identifying different types of chemical reactions. What we have in this chapter, the chapter has identified 4 or 5 types of chemical equations. One is the so-called combination reaction. This is just when two compounds come together to form some other compound. 2, let's see, there's some such thing as a decomposition. This would be like the opposite, something comes apart, decomposition. Then another one is the so-called single replacement. This is where one element replaces another. Like you might have a compound that has 2 elements, but then another element comes along and pushes in and replaces one of the other ones. It's kind of like 2 people dancing, and then someone cuts in on the dance and steals the dance partner. It's a swapping. And the next one is called double replacement. This would be like 2 dance partners, and then they both swap partners. Okay, and then the 5th one is called neutralization. Okay, this one a base and acid react to produce a salt and water. Okay, these are just, I mean, I'm sure there are other specific types of chemical reactions, but these are just 5 that this particular chapter has decided it's going to talk about. And it's just a way of categorizing. A lot of chemistry is just categorizing reactions or things that happen with elements and all that. Okay, let's just go and see what we got. So the question here is, which of the following types of chemical reactions is illustrated? So here's an example. Nitrogen gas plus hydrogen gas react to form ammonia. Now, ammonia is a gas. You might think ammonia is something you get in a bottle at the store, but the ammonia you get in the store is actually water that has ammonia gas dissolved in it. Okay, well, this is obviously a combination reaction because you got 2 things coming together to combine and form something else. Okay, let's take the next one. Potassium. This looks like a carbonate, but I'm not sure how to say that. Potassium hydrocarbonate? Anyway, this reacts to form potassium. This is obviously not a balanced equation. To form potassium carbonate plus water. In this case, a water as a vapor. It just means that there's enough energy in this reaction. Plus carbon dioxide. Okay, also is gas. Well, I've never heard of this reaction before, but It's obviously just an example of a decomposition, since they're just trying to put it in different categories. Because you have one substance and it turns into three substances, it's decomposing. And in this particular case, they put the triangle. That shows that this is taking place with the addition of heat. So you have to add energy to it. This might be, you might be burning it or something. The assumption might be on a reaction like this that it's going to release heat. But I suppose if it says nothing at all, you can't tell one thing or another. But when it got the little triangle, that means that it does take heat to do it. Okay, the next one is zinc, solid, plus hydrochloric acid reacts to form zinc, chloride, aqueous, which means it's dissolved, plus a hydrogen gas. Okay, this is really zinc being dissolved by hydrochloric acid. Okay, but I'm going to say that I'm going to say that this will be an example of a single replacement, because you can kind of see that the zinc is taking the place of the hydrogen here. Now, you're not going to get zinc chloride unless you evaporate all the water. The hydrogen gas is going to go away. But and what's not clear here is exactly how this happens. When I say exactly, what I mean is step by step, mechanically. If you have a block of zinc in a solution of water which has hydrochloric acid in it, how does this happen that the zinc atoms in that block of metal actually start breaking away and floating off into the solution? And apparently the hydrogen atoms in the solution, because this HCl turns into H plus and Cl minus in solution, this H plus, you have this block of zinc. It's just zinc everywhere. It's just a block of zinc. And the hydrogen gets in here and dissolves it. It liberates some of the zinc from the block, and in doing so, the hydrogen gas is formed. But that's more complicated. We don't need to get into that because all we're trying to do here is look at different types of reactions. Okay, the next one is aluminum, chloride, aqueous, plus silver nitrate. Silver nitrate, this is very common, used in the lab on these types of experiments. Okay, and this makes aluminum, nitrate, plus silver chloride. And that's a precipitate. This is obviously the double substitution. You can see that the silver and the aluminum are trading places. And what's happening is when the silver, the aluminum, so what's happening here is that this is originally aqueous, which means in the solution you have aluminum, we know is going to be a +3. We got chlorines, we got silver, which is +1s, and we've got chlorine and nitrates, floating around in the solution because these are all aqueous. Now what's happening here is when the silver and the chlorine get close to another to bump into each other, then they stick to each other. They don't bounce off and separate. They actually stick and form a it forms a molecule, and then that molecule it drops to the bottom of the material, or it bumps into other silver chlorides, and they get a solid forming at the bottom. I believe it's a powder. Now, the real question is, why do these stick together? It's a solubility issue. It's in water. You've got water molecules, but the water molecules don't break it apart the way they would in the aluminum chloride. They break that apart, and in the silver nitrate, they break that apart. But the water molecules are not getting in here to separate these, and can't say exactly what a good explanation for why that is. But once again, that's not exactly what we're talking about now. There are solubility rules, and but we'll get into that later. Okay. So right now we're just looking at an example of a type of reaction and saying that it's listed as a double replacement, but actually these were just solutions of various things, and one of them formed a solid. That's because one of the items got replaced with the other one. And that essentially leaves you with aluminum nitrate left over, even though it's dissolved. It'll eventually reform if this water evaporates. Okay, and so you can see here, this is obviously one example of each type. So we know what the other type's going to be even before we write it down. It has to be the neutralization reaction. H2SO4, that's sulfuric acid. Reacts with sodium hydroxide. This, I believe, is called lye, used as a cleaning product. Caustic type of product. Okay. This forms, sodium sulfate, aqueous, plus H2O. Looks like I ran out of room. That says listed as a liquid. Okay, so the idea here is this is a base now, and this is an acid. Now, when this goes into solution, you're going to end up with H pluses and an SO4 minus, 2 minus. When this goes into solution, you're going to end up with an Na plus and an OH minus. The presence of a lot of OH minus is what is called a base. And the presence of a lot of H plus is what makes something an acid. Now, if you end up putting a lot of OH and H plus together, these are just going to snap together to make water, more water. And that's what's happening. That's all that's happening in this neutralization reaction. It gets neutralized. Anything that has a real strong concentration of H plus is highly reactive. That's why an acid is highly reactive. It'll burn you. Something that has a very large concentration of OH minus, of the hydroxide ion, is also very reactive. It will also burn you, but it's like an opposite to the H plus because when they annihilate each other to form water, which does not burn you, because that's what you're made out of. That's that's neutral. So the whole idea about acids and bases is it's a scale that tells you whether or not something like a water solution has an overabundance of OH minus or an overabundance of H plus. And normally they have very small, only very, very small amounts of either of these, almost essentially zero, because of the way they annihilate each other. The only way they're not exactly zero, has to do with thermodynamics. In other words, if you have a solution of water, and I guess for the purposes of this, I should actually be drawing it like this, HH, kind of like a bonding thing. If you have a solution of water, and it's at room temperature, that implies there's a certain amount of energy. Things are moving around. And what happens, every now and then you get a collision where this thing breaks. It's like potato chips in a bag, and you start banging it around. They break. And that produces a separation. And the hotter it is, the more it will break. The thing is, potato chips never go back together, but these will actually go back together. It's a dynamic equilibrium. That when they just happen to get next to each other because they're moving around, then they'll stick to each other. But then if they get bumped again, then they'll split up. And then so there's just it's called a dynamic equilibrium because both events are happening at the same time in this large mass of tremendous number of molecules in water. Okay, let's go to the next section. That was pretty light, okay? Just talking about categories of reactions. Not a lot going on there. Let's look at the next section and see if it's more interesting. It says, predict the product of the following reactions and balance equations. Well, let's just see what it looks like. Aluminum, which is a solid, reacts with oxygen, which is a gas, under the action of heat to produce. What's that going to produce? Well, I happen to know that aluminum, in the presence of oxygen, makes aluminum oxide. This is the corrosion that happens on the aluminum storm door. And because of what we know already about this is a metal, this is a non-metal. They're at the ends of the periodic table, and they react according to the valences. And it's going to be Al2O3, because aluminum is in the column that's 3 away from the noble gas, so it likes to form +3. Oxygen is 2 away from the noble gas. It likes to form -2. Aluminum is 3 away, from the opposite side. So it likes to form +3. It's actually 5 away from the noble gas. Okay? So if it lost all of its electrons, it could gain 5 electrons and becomes -5, or it could lose 3 electrons to become +3. Anything that's closer to the left side of the periodic table tends to lose the electrons. Anyway, so that's what's happening in this case. It's Al2O3, aluminum oxide. Okay. Okay. Now, and this would be a combination reaction. They come together. Could call it. I call this oxidation. That's another type. That's just a name of categorizing a reaction. Okay. Lithium, hydrogen. Okay, now this is an interesting reaction. Now, I would have no clue what this would do, except I could tell that lithium and potassium are very similar because they're both alkali metals, and they gave us a reaction earlier in the previous section of an example of a decomposition of a potassium hydrocarbonate. I'm not even sure if I'm saying this right, but if this is lithium hydrocarbonate, this could form, just using the analogy of the previous one, it could form a solid, which is lithium carbonate, because the CO3 is -2. Apparently. Now, one thing I didn't write down, this was a solid. Okay, this is a solid. Now, this is going to form a gas, H2O, and CO2. I'm not familiar with this reaction at all. I wouldn't have been able to even guess that this would happen unless the potassium was a previous example. Anyway, so I'm just going to guess that this is a reaction. Okay. Let's go to another one. Okay. Here's another one. Aluminum. There's that same hydrocarbonate, or whatever it's called. There's 3 of them. You can see that each hydrocarbonate is a -1. Well, this, I'm going to just guess that this could do exactly the same thing when this breaks down. I might be wrong, but you can end up with an aluminum carbonate. Now, that aluminum is +3. So if I might get this wrong, but if the aluminum were 3+, and if a CO3 was a 2-, then this would be one of these cross things. This would be a 3 and a 2. Yeah, I don't know. Oh, they give us a clue that there are actually 3. They actually tell us on the right-hand side that there's going to be 3 items. And I'm just following the previous thing. I'm just going to put in the H2O, and I'm going to put in the CO2. And this would be interesting as an example. I'm just guessing this, but now the question is, can it be balanced? Okay, is it possible for such a reaction to even take place? And so I'm going to give a balancing exercise. I'm going to put a 1 here and a 2 over here. That balances the aluminums because they appear only in one item. Now, let's check on something else. Like, let's try to balance off something else, like the hydrogen, for example. Hydrogen here, we can see that we've got 3 or 6, so that's going to have to be 3. Okay. Then let's balance off the carbons because, oh, now the carbons are showing up in 2 different places, but that's okay. We're going to balance it anyway because we're going to see that the total carbon on the left is equal to total carbon on the right. So the total carbon on the left is going to be 3 times 2, or 6 carbons. 6 carbons. On the right, it's going to be 3 carbons. So there's got to be 3 more. So this would have to be a 3. Now there's only one thing left, and that's oxygen. And this forms our double check, whether or not this would even be possible for this reaction to ever take place. Now, number of oxygens is going to be 9 times 2, or there's 18 oxygens on one side. On here, there's going to be 9 oxygens here, there's going to be 3 oxygens here, and 6 oxygens here. So that does equal 18. So this does seem like a possible reaction. So if it's possible, then I probably guessed it right. And of course, I was just copying the previous thing. Okay, we're at 23 minutes, so let's just see about if we can do the next section here. It says, predict whether or not a reaction for each of the following based on activity series. Aluminum, or whether or not a reaction occurs. Okay. Well, the reactivity series, we're going to have to write it down because I noticed it was in this section, this chapter, and I that have not memorized reactivity series. You'll probably be provided with this as a reference. So let's just say something about the activity series. According to this is the relative activity series. Lithium, more active. The potassium, barium, strontium, cadmium, sodium, magnesium, aluminum, magnesium, zinc, iron, cadmium, cobalt, nickel, tin, lead, hydrogen, copper, silver, mercury, and gold. Okay. Now you'll notice there that there's something interesting about this. You'll notice gold is the last one. Now you know gold doesn't rust. It's very stable. That's why we make rings and things out of it. Jewelry is made out of gold. And also silver notice is very similar. And even copper. Copper was one of the first metals that was discovered in nature, and people made silver, jewelry out of it. That in the southwest of the United States, Indians, Native Americans could find copper in the mountains, and they could make metal objects out of copper simply by hitting it with a hammer, because you can find it in a solid form already all by itself. Iron, for example, you don't find iron in the ground. It's because it's rusted away. That's because it has reacted. Things like this always be reacted. Then as you get towards the end here, you'll find things you could actually find these metals all by themselves. Mercury, I don't know that you tend to find it all by itself. It's a metal. I mean, it's a liquid at room temperature, so I'm not sure what the history is of when that was first discovered and all that. Oh, okay. So, taking that as a starting point, let's just look at the first one. Aluminum foil, that would just be a solid aluminum, is added to iron sulfate, iron 2 sulfate. So that's Fe. That means that the valence state is going to be 2. And sulfate, SO4, if I remember correctly, is SO4 minus 2. So it's FeSO4, ferrous sulfate. Because iron is either +2 or +30 on the valence. Okay, now, will the reaction occur? Well, let's look at aluminum. Aluminum is more reactive than iron. So yes, what that means is the aluminum is going to take the place of the iron. Okay, the aluminum wants to get in with the sulfate more than the iron does. Okay, this is my analogy. If this was these two, iron and sulfate, were dancing, and then aluminum came along, aluminum wants to get in there. Now, the reason is because aluminum, according to this chart, the aluminum is simply more reactive. But what's happening here is, this is a solution. So we have iron, and it's 2+, and we got sulfate, and it's 2-. I don't know if I should have the parentheses around it. Maybe I should. Sulfate, 2-. Doesn't matter in this case. It's an ion, right? Sulfate ion. Okay. Now, aluminum, we know, has a valence +3. Yeah. So aluminum, if aluminum is to form with the sulfate, it would be one of those, if it was to form as a solid, it would be Al2SO43. I'm sorry, 3's in the other place. Okay. In order, if it was an ionic compound like that. Now, the aluminum is willing to give up electrons, okay? And if the aluminum, when it gives up an electron, see, this has to do with the amount of energy required to remove an electron is different on different materials, and that's the so-called ionization energy chart, and that's in your book, Ionization Energy. And a particular atom like lithium has got atomic number 3. It's got 2 s electrons. Okay, and then it's got two 1s electrons, and it's got one 2s electron. The 2s electron takes a certain amount of energy to pull it off. Well, what that also means is the amount of energy it takes to remove that is exactly the same as the amount of energy that will be released if that electron comes back down onto the lithium. In other words, the lithium plus ion, after you've removed the electron, now is a magnet for electrons. It attracts electrons back to it because it's got the plus. And it will attract them with a certain force, okay, a certain force. Now, this iron sulfate, when these split apart, this SO4, the sulfate ion is negatively charged, okay? it will be attracted to various positive ions, such as iron or aluminum ion, with different amounts of force, depending on the attraction of that particular ion. See, an ion might have a certain charge state, like a lithium ion, remember, is just a +1. A potassium ion is also +1. But that doesn't mean that one of them might exert a stronger force, okay? And the reason is because you can get closer into the nucleus. Lithium is only an atomic number of 3, so this has to do with the atomic radius of the lithium ion. It has a relatively small atomic radius. That means that if you had another relatively larger, like this, let's say, is a larger ion, and this is a small lithium +1, because it can get closer to it, it's more strongly attracted to it. And that's because the force of electrical attraction it's the inverse of the square of the distance. Okay, it can get closer to it. So this is really the reason why this is more reactive. It really has to do with the fact that it's smaller, and it's a +1 ion, but it's smaller, and that means other objects that are negatively charged can get closer to it, and they're more strongly attracted to it. It's stronger. It's a stronger force. These are electrical forces, but if we made a crude analogy, and these were all like little magnets, it's like one of these magnets would be a stronger magnet than the other one. So and the magnets, of course, the positive and negative poles of a magnet attract. But if you had a more powerful magnet, it could displace the other one. So in this case, this is an example where we're going to predict that the aluminum is more reactive than the iron. That's all. You'll also notice that the atomic number is just generally tending to increase in this chart. It's small here, it gets bigger. That's like an atomic number of 26. And then gold is probably an atomic number in the 50s. Anyway, that's just a little theory about where the different reactivity series, where that order would come from. Okay, now the next one. But in this case, we don't need to know all that. We just need to know that there's different reactivity. Iron wire, iron wire. So the idea is iron as a solid and aluminum sulfate. Aluminum? Huh. We were just talking about aluminum sulfate. Okay, so aluminum displaces iron, but now, they're just doing the exact opposite. Now, iron and aluminum. So the iron cannot displace the aluminum. So if you put iron wire, then it's not going to form this was the Al2SO4 3. Okay? Aluminum sulfate solution. You're not going to get the iron to displace the aluminum. In other words, you're not going to get this iron sulfate to form. Okay? Okay, so the real answer is no. This is a yes or no. These are yes or no questions. Will a reaction occur? We're going to predict no. Okay. Manganese and acetic acid. Okay, manganese, that's Mn. Acetic acid. This is vinegar? Acetic acid and vinegar. What is the formula for acetic acid? I wish I could remember. I don't. So we're going to skip over that one. Gold in sulfuric acid. Well, nothing's going to happen because gold doesn't react with anything. Okay. Gold. Sulfuric H2SO4. Oh, acetic acid. Finally, I'm going to come back to that one. I just got. Okay. So in this case, you're comparing the reactivity of gold to hydrogen. Okay. Gold is less reactive. Nothing's happening. Now let's go back to the other one. Manganese. Now, acetic acid, it's an acid, so what it's going to replace is hydrogen. I forget what the other compound is on acetic acid, but manganese is more reactive than hydrogen, which means it will react in the acid. Or in other words, acids will dissolve all of the things that are less reactive I'm sorry, the things that are more reactive, and it will not dissolve those things on the right. These are the metals that don't dissolve in acid. These are the so-called noble metals. They form and they're used for jewelry because they don't rust. Okay, zinc and hydrochloric acid. So this is the same thing. We want to know whether how zinc will react with in an acid. Zinc is more reactive, so zinc will dissolve in acid. That's anything that dissolves in an acid. That means if left to the elements, because we have acid rain, if left to the elements, it's going to decay. Aluminum siding will decay because it reacts with. It's more reactive than an acid, hydrogen. Okay, a chromium strip. Cr, chromium. Chromium, calcium, cobalt, cadmium. It's not even on this thing. Anyway, a chromium strip is put in water, and I'm going to say no. Honestly, I'm not sure. This looks like a trick question. It's not even on the reactivity series, but I'm going to say no because we know chrome is something that you actually coat things with so that they don't rust. Like cars, you put chrome on them. Okay, so we're running over a little bit, so that'll be the end for today. Okay, thanks.